my name is Chris Sensor, and here today to talk about damping. We're going to talk today about damping, in particular viscous damping. So damping has a lot of different names. You have the viscous damping coefficient, damping ratio, percent critical damping, damping factor, loss factor, and it goes on and on. In this presentation, we're really going to be focusing on damping terms that are in test lab, where they come from, how they're related, and some caveats for that relationship. We can see here on the side, this is how damping works, right? This system on the left is an undamped system, no dash pot in it. And you can see the amplitude doesn't reduce over time. We start to add damping to the system, and you see over time the amplitude diminishes, but you'll notice that the frequency does not, right? We still maintain the same zero crossings as the undamped system. Now, here on Earth, we never really see undamped systems. Everything has a little bit of damping to it. So any system that we deal with here on Earth, even this system on the left, in reality, there's a little bit of air here. So eventually this system will damp out too. So it's in everything that we deal with, and it's an important thing to understand. We talk about damping of complex structures, but we're always bringing that damping back to SDOF systems, single degree of freedom systems. And a single degree of freedom system has a mass, a spring, and a damper. And sometimes there's base excitation, sometimes we're dealing with free vibration, where you have maybe an impulse that gets your system moving. And what we have is a force, because this mass is moving. Force, there's some acceleration here that's happening as the mass moves up and down, changes in acceleration as we saw in the previous slide. And so we have a force that's occurring here, right? F equals ma. Forces we usually talk about in newtons. Mass, we're generally talking about grams or kilograms. We have this viscous damping factor here. This is modeled with a dash pot here, and that's in newton seconds per meter. We have the spring coefficient K, or stiffness as we frequently call it, and that's newtons per meter. And then we have displacement, which is typically measured in meters. All of these have conversions into the, well, we used to call it the imperial system in school, but I think might as well just call it the American system, because we're the only people still using pounds and pounds force, pounds mass. That gets a little confusing because you need to convert pounds mass to pounds force when you're doing some of this stuff. The SI system makes it a lot easier to do the math. So by definition, what damping is a decrease in amplitude resulting from energy loss. And there's a lot of different types of damping. There's damping that occurs from friction, when you have two bodies working against each other. You have viscous damping, which is generally a fluid that is affecting energy loss. But there's other kinds of damping too. We have drag, which is aerodynamic forces, magnetism. There's structural, or what we call hysteresis damping. You have damping in electric circuits from resistors. And there's even damping that occurs at a subatomic level. It's called radiation damping. But we're really only talking about viscous damping generally when we talk about structures analysis. Why? Because viscous damping is very easy to understand. So we want to try and compare everything we do with these big mass distributed systems that we work with back to this SDOF system. We have this viscous damping coefficient C. As I mentioned, it's in Newton seconds per meter, and it's proportional to velocity. But the problem with this coefficient of viscous damping, or the actual real damping value of the system, is that it doesn't really give you any insight into the system behavior. So we have to look at the equations of motion to really understand that. And what we get into is trying to understand damping universally, not just in terms of the damping coefficient. What that gets us to, if we look at time signal here, we can see the effect of different amounts of damping, or different percentage dampings in each of these time traces. The funny thing is, this is percent critical damping, or the zeta value. We'll talk about that in a second. Each one of these traces was generated with the same damping coefficient. So that's something that's important to understand. You can have the same damping coefficient, but depending on the mass of the system, if you vary the mass, you can get very different percent dampings in a result. And that's because of this here, right? We have this idea of critical damping. And what critical damping is it's the threshold between an underdamped and an overdamped system. And when damping occurs at critical damping, you're returning to an equilibrium state as quickly as possible, right? The critical damping factor is determined solely by the stiffness and mass of the system, okay? So again, looking at these were all the same viscous damping coefficient, but by varying the stiffness and mass, we get different percent dampings. And this is what we're typically looking at, is this percent damping. Well, where does that come from? Okay. This zeta value, most typically in vibrations, we use this Greek letter zeta. And what we have is the actual damping coefficient divided by this critical damping factor. And it describes how a system will decay after being excited. And what we're looking at here is the same graph as up here, but in the frequency domain instead of the time domain. So you can see the effect on damping reduces the apparent amplitude of the system in the frequency domain, right? If we look at this, all of these started at the same amplitude at 0 or very shortly after 0, but the damping has an effect on the apparent peak. So if we take a look at what happens when we are critically damped, where zeta equals 1, so the ratio of the viscous damping coefficient to the critical damping are the same, we end up with a system that doesn't really oscillate. We have our initial disturbance, and then we return to 0 as quickly as possible. There's two other cases. We have the underdamped system, which oscillates, and that happens when zeta is less than 1. So what that means is the damping coefficient is less than the critical damping of the system. And then we have an overdamped system, which also doesn't really oscillate. So the difference between underdamped and overdamped is, or critically damped and overdamped is, we've got some kind of maximum excursion here, and it goes back to 0. When we're overdamped, there's no excursion. There's only, I guess you could say there's one oscillation in a critically damped system and no oscillation in an overdamped system, as opposed to underdamped, which can oscillate many times. So what we're typically dealing with in the vibration world is underdamped systems. There's some exceptions. There's some exceptions to that. When we're designing things like suspensions, a lot of times what we want to have is a suspension that's critically damped. So we're returning to 0 or over damped so that we're returning to zero as quickly as possible. But most of the time in vibration studies of what we're dealing with in the vibration world, we're looking at underdamped systems. And that brings us to our first description of damping here is the Q factor. And you might have heard of this before, but the Q factor is by definition based on energy loss. So we're looking at the decay time for energy over the time to oscillate 1 radian. And that's the definition of the Q factor, and it's related to zeta. And so Q gives you an idea of how sharp this resonance is going to be. The higher the Q factor, the sharper the resonance. It has an inverse relationship with zeta. So the higher the Q factor is, the lower the percent critical damping is. Most of the time, we take a look at this and we try to get an estimation by using this 3 dB down method. Now there's some caveats here. We'll talk about 3 dB in a minute. There's some caveats here with this relationship, and we'll talk about that too in a little bit. But basically, the higher the Q factor is, the lower the energy loss, and the lower the Q factor is, the higher the energy loss. The 3 dB down method, or half power method as it's sometimes called, 3 dB down is half the power of the peak. What we're looking at with this half power method is the ratio between the resonant frequency and the width of the peak. So you can take a look at this in test lab and identify exactly where this half power point is. And we'll see in this particular case, we've got a Q factor of 14 for this peak. But you can always hand calculate that as well. There's some caveats to that as well. This half power method doesn't work with close modes, right? What's the actual contribution of this mode to the damping versus this mode? There's really no good answer to that question, so this half power method falls apart when you have closely spaced modes. Definitely need to use a curve fitter, because the curve fitter can separate the peaks and take a look at the influence of the residuals from each mode on the other. And we also have the Nyquist method or circle fit method. And what we're looking at with Nyquist is we're plotting a Nyquist plot, which is the real versus imaginary for each frequency. And you can see with an S-stop system, you get a nice circle. And what we're generally looking at with the circle fit is, again, we're looking at, it's a little easier to identify the resonance points here. So you can use the half power method here a little more precisely, because you can fit an exact circle to this. And so you know with much finer frequency resolution exactly what the amplitudes are, or the frequencies rather, at either edge of this circle. So what we're looking at with Nyquist is the width of the circle, and where the circle is the widest, that frequency along this diameter here is our F1 and F2. And then our center frequency is where this circle intersects with the zero line. Okay, so the main advantage of this circle fit over this 3 dB method directly from the peaks is this 3 dB down method really falls apart when you don't have adequate frequency resolution. Loss factor is another way to describe damping. We relate this to 1 over Q, but what loss factor is really looking at is a hysteresis loop between stress and strain, and it's a good measure of a material's damping. And what this is really looking at is how much energy gets dissipated after 1 radian, if you're looking at the time domain. And this relates directly to Q, right? Q is also based on energy dissipation. So it's just a different way of looking at Q, right? So if the Q factor is higher, that means lower damping. N has a direct relationship. So eta is a direct relationship with the Q factor. It's derived in the same way, but it has a more direct relationship with damping, right? So if eta is higher, you have more damping. If eta is lower, you have less damping, as opposed to the Q factor, which has the inverse relationship. There's another factor in test lab. It has a couple different names. This is a lowercase delta, but you have tan phi, tan delta, or your loss tangent. And what that's really looking at is the relationship between stress and strain, and looking at this lead lag between stress and strain in material. In test lab, we're always calculating the Q from a cursor, and then any other factor that you put up on the screen is just based on this conversion. One of the issues with this is basically if you have more than 10% damping, these all fall apart and diverge. So for highly damped structures, this doesn't work out very well. For lightly damped structures, which is generally what we're dealing with, less than 10% damping, this tends to hold up pretty well. And again, this is in the test lab software. If you're putting up any one of these factors, what we're really calculating in the software is the Q factor based on the half power method, and then using these equations to convert to anything else that you might display on the screen. And here's where this method falls apart, right? I have 3 different spectra here. All of them were derived from the same Estoff system, same mass, and I think in here the damping factor was varied a little bit, but different delta frequencies is the main takeaway here. Each one of these different delta frequencies causes error. So you can see the finer delta frequency, 1/8 hertz resolution basically, it matches up pretty well. 2% damping, 2.03 calculated in the software. However, we start to have divergences. So with 1 hertz resolution, we've got a significant difference, and 2 hertz resolution, also pretty significant difference in damping. And this is all due to the fact that the half power method, you need to have a data point at your half power points. And if you don't, you got to use the next data point. So that can cause some issues. So now let's take a look in test lab, and we can see some of these things. Okay. For example, let's look at 2% damping. The majority of this 8-second long time sample, now again, this is perfect, right? It's perfect because I generated it in Excel. So I have no noise inherent to this. It's just a perfect time sample. In reality, though, if I was measuring this with accelerometers and stuff, and you have electrical noise and all kinds of things, big issue is you're measuring noise for most of this time sample. So to get 1/8 hertz resolution, you're measuring mostly noise, which can affect your result. And what we're looking at here is, again, it's the same signal I started with, just truncating it at different time lengths, which gives me different delta frequencies in my FFT result. And you can see the difference in the damping percentage here based on a half power method. Even the 1/8 hertz resolution, again, I generated this, it was an exactly 2% damping Estoff system, and I'm not calculating 2% damping here. And you can also see that the different spectra, how leakage is affecting these results of not having this perfectly periodic within the window and all that digital signal processing stuff. You can also see, if you look at your Nyquist plots, these are the same curves, just displayed in a Nyquist plot. And a Nyquist plot is the real versus imaginary at different frequency points. So you can see, if I look at, for example, 35 hertz, right? That should be basically exactly the resonant frequency of the system. It should be at the bottom of this circle here. And as I get higher in delta frequency, I get a different resonant frequency. So that's not good to begin with, right? It should be a perfect circle. So how do we fix that? Well, one thing we can do is actually apply a curve fit to this. So we can see here, this is Polymax curve fitter. I pulled in the 4-second long time sample. All right, and if I delete this, I get my stabilization diagram here. I can even increase the model size if we really want to take a look at that. But you see, it doesn't go any higher. It just stabilizes. It's an S-stop system. So we pick this pole, and we can see this pole is perfect 2% damping. And we can save that mode shape away. And that's what I did for a couple of these. And what you see here is, if I'm looking at, and that's what this graph is. This is my quarter hertz resolution spectrum from this decaying sinusoid here at 2%. So this one right here. And when we synthesize the FRF, you can see it fits this perfect curve to it. So we get an exact damping. And if I look at each one of these mode sets here, 35.58, 2% damping, that's with 4 hertz resolution. 2 hertz resolution, 30.58, 2%. And 1 hertz resolution, still 35.58 and 2%. So you can see this result is an approximation, and sometimes a wildly different approximation than what the actual system damping is. So you have to be careful, right? So very, very dependent on frequency resolution. But that's how you would display the damping value from a cursor. So that is everything I wanted to talk about.